Hey guys, Mr. Backberg here. In this video we're going to be looking at the natural base, e. So the natural base, e, is a number that shows up a lot in physics and in calculus, and we also see it show up in applications such as exponential growth or exponential decay or compound interest type problems. So e, it's actually named after Leonhard Euler, who is a pretty famous Swiss mathematician. Now e is a lot like pi. E is a symbol used to represent a number, and it's an irrational number. It never repeats itself and it never terminates, so it's difficult to say what number e actually is, but just like pi has an approximation, e also has an approximation. And we can come up with that approximation by using a limit. So we can use this limit definition to help us approximate what e is, and I'm going to use my calculator to help me out. So in my calculator, I've got that 1 plus 1 divided by x being raised to the xth power, and I'm going to look at a table of values in here. So I'm going to go second graph. Now we're looking at the limit as our x values increase. So I'm going to keep increasing my x values in this table, and I'm going to look at what number my y's start to approach. So I've taken my x values all the way above 10,000, and we're getting a y value of 2.7182, and that's a pretty good approximation as to what e actually is. Now, as we're talking about this e value, we're going to be looking at exponential functions. And any exponential function, f of x equals a times b to the x, can be rewritten using this e. So f of x equals a times e to the kx power for any appropriately chosen real number k. Now, with this exponential function, if our a value is positive, and if our k value is also positive, then this is an exponential growth function. But if our a value is positive and our k value is negative, then this is going to be an exponential decay function. So we're looking at performing some transformations with this function, and we're thinking about our f of x equals e to the x function. And as we look at the first one, we're given g of x equals e to the 2x. So we can really think about this new function as our f of x function, but instead of just having x, now we've got 2x being plugged in. And what this is going to do is a horizontal shrink by a factor of 2. And I'm going to graph that out on my calculator to confirm its behavior. So in my calculator, I've got my y equals e to the x, and I've got y equals e to the 2x. When I hit graph, I can see both pictures of my functions in there, and we can see that my red graph has gotten horizontally shrunk from that blue graph. Now, as we're looking at letter b here, where we've got h of x equals e to the negative x, we can think about this as our function with a negative x plugged in. So this is going to be a y-axis reflection. And again, I'm going to graph this one out on my calculator to confirm the behavior. So in my calculator, I've got my y equals e to the x, and I've got y equals e to the negative x. Now when I hit graph, I can see that my blue graph got reflected around the y-axis to give me the red graph. And then for our last one, letter c here, we've got k of x equals 3 times e to the x. So we can think about this as 3 times our original f of x function. So this is going to be a vertical stretch by a factor of 3. And one more time I'll graph this out on my calculator just to confirm the behavior. So in my calculator I've got the y equals e to the x and y equals 3 e to the x. When I hit graph, I can see that my red graph is getting taller faster, so it's a vertical stretch by that factor of 3. That's going to be it for this video. Thanks for watching.